Next up, we have Michael Bennett talking about energy-efficient Ethernet. Michael.
Okay, thank you. This is going to be at a little bit different layer than we were just talking about. I'm going to talk about, sort of frame the discussion about why you would have network energy or interest in even network energy efficiency, and then also explain a little bit about energy efficient Ethernet, define it, talk about background, how it works, what the trade-offs are, and so forth. And then how it will work with optical Ethernet, and then wrap up with some opportunities for development and final wrap-up. But before I get into that, I need to make my disclaimer statement. So essentially, anything that I talk about with respect to IEEE here is just my own personal view and not any formal position or explanation or interpretation of the IEEE. So network energy efficiency. It's not exactly the lowest hanging fruit in the energy efficiency world. If you have been following how to make your, for example, your data center more efficient, you wouldn't think of using the network as the first place to start, thank you, to achieve energy efficiency. It starts with a process, you make some baseline measurements, analyze the results, and then make changes and then improve on that. So the changes that typically tend to make the bigger improvements have to do with optimization of airflow or using more efficient power supplies and that sort of thing. Then when you get beyond those, choosing more efficient information communication technology equipment would be the next place to go. One of the things that I encountered along the way when developing energy efficient Ethernet, people would ask the question sort of, you're talking about a few hundred milliwatts or a watt or two, so why bother? Is it really worth it? Is it worth it to go through 3 or 4 years of standards development and then create a standard and then have the industry go off and build it for a few watts? But when you think about Ethernet as a technology, it's probably, arguably, one of the most successful technologies in the market today, over 1 billion ports in the market. So when you look at the numbers that way, it adds up. And to put that in perspective, excuse me, we're talking about data center electricity alone in 2010 accounted for over 1% of total electricity use. So it does add up. The idea here with making network energy efficiency is to make the network scale with utilization. So when the utilization goes up, then the energy goes up, consumption goes up, and likewise when it goes down, then the consumption goes down. Again, just trying to make the point about how much savings can come from the network, about 5% of data center electricity. Back in 2006, that accounted for about $225 million spent in energy. So you still might have the question, well, why does that matter? If you could achieve additional efficiency from your network, you might qualify for an incentive. And the EPA encourages that, and in this example, New York State actually did offer an incentive. And usually those incentives work in the way that if you cross some threshold in savings, then you're eligible to receive funds, and then you could take that and invest it in even more savings, try to make your network more efficient or your data center more efficient. This is just a simple cartoon to show what we're aiming for with energy efficiency in the network, just to make the network proportional to the utilization. So as utilization increases, so would the power. Now this traffic chart I chose to use as an example over a period of time. I'm sure most of you are network operators. You've seen this sort of chart before, and you see the nice diurnal pattern over time. And the point here is just simply that the networks are not full-on 24/7, 365, that there are some valleys in those utilization charts, and each of those valleys represents an opportunity to save energy. So even in this particular case, it's Akamai data set, high transaction rate network, that there were valleys there, and each of those is an opportunity to save energy. And then just to translate that into dollars, energy cost is still a significant expense. Again, in data centers, I'll just point out the bottom line, or the biggest number here, which is, again, this is from 2006, but the entire United States spent about $4.5 billion in data center energy costs. So it does add up. Now, getting into Ethernet, you might wonder, well, so how much can I save from a network interface? And depending on how you slice the network interface, if you look at just the physical layer portion of it, that part could be reduced by 90%. And if you look at more of the network interface, you can get, on the average, about 70% savings there. And you can even get more savings if you're clever about how you design your system and take advantage of LLDP, and I'll talk a little bit more about this in a slide that I refer to in a few moments. So let's talk about energy efficient Ethernet, or EEE. Simply, it's a method to make the energy use scale with utilization. It was defined back in actually published in 2010, and it's currently defined in IEEE Standard 802.3 2012. And again, the premise is that the links are not fully utilized, or they have idle time, and so those are the opportunities to save energy. It's defined in the copper interfaces, or I call them the base Ts, with the exception of backplane 40 gig. The 40 gig, 100 gig backplane, next generation optics, and 400 gigabit Ethernet are all in the process of defining an energy efficient mode for those projects. The technique is called low power idle. So as the name implies, when there's idle periods in the network, it can go to a low power mode. And for optical Ethernet, or speeds greater than 10 gigabit Ethernet, there's a new concept we introduced called fast wake, and I'll talk about those more in detail here in a moment. Again, how does it save energy? Well, simply power times time in the active and idle states. You add that up, and that's your energy use. So as you might see then, if it's not obvious, that it's actually energy efficient to go to a higher speed because the bit times are shorter. So one way to achieve energy efficiency is just simply to go a higher speed network. And this is just a picture to show where in the Ethernet stack EEE fits. So again, the idea is to send the data as quickly as possible and then switch into a low power idle mode. And the energy savings comes from cycling into LPI when there's no data to send. This gets into a little bit more detail about how EEE works. The transmitter would be, in this case, where we have the red block talking about idle or data. So if it's sending data, it's sending data, and if there's no data to send prior to EEE, that would be normal idle, and you still are utilizing full power even when you're sending idle, an idle signal. With EEE, when there's no data to send, the transmitter would assert LPI, which means that it's going to send a sleep signal, indicating to the receiver that it's time to go to sleep, that as soon as the sleep indication signal stops, the line's going to go quiet. So at the end of, I've got these little parameters underneath the blocks titled T sub S for sleep timer, or T sub Q for quiet time. So the next step in low power idle would be when the line goes quiet. And it stays quiet for T sub Q. And then when that timer expires, a refresh signal is sent to the receiver just to allow it to maintain coefficients and be able to come back up to the active state as quickly as possible. And it continues through that cycle until there's something to send. And then when the transmitter determines there's something to send, it will send an alert and a wake signal. And the combination of those two times is represented by T sub W phi, so TW phi. And then there's an option to extend that time by sending an idle signal, and then it goes on into the active state again. Now, why would we have the second parameter that we call TW which is just essentially after the receiver wakes up, you still start sending some idle signals and allowing those idle signals to come in before you actually start to receive data again. Well, if you can accept the additional time to wake up, that creates an opportunity to allow the system designers to shut other parts of the system off, but then take that additional time to wake everything back up again. So it enables people who want to design systems that are more efficient to do so. Now, the trade-off here is that it takes a little bit more time to wake up. You may wonder what these wake-up times look like, and I've included a few here to give you sort of an example, starting with the worst case, which is the 100 base TX, which is in the order of 30 microseconds to wake up, and then in the example 10G base T, about 8 microseconds to wake up. And they're actually even faster with the faster interfaces. The other thing here is, so with the link partners, again, remembering that these are defined for twisted pair interfaces, the link partners will negotiate and advertise EEE capabilities during auto negotiation. Once the link is up, you can still communicate using LLDP to notify the link partner of the parameter changes. So if you started up and went with, for example, the minimum wake-up time, the TW phi parameter, and then later determined that you wanted to go into a more efficient mode, you could actually change the parameter in the local system, would send an LLDP frame to the other side, and then actually increase the amount of time it takes to wake up. So you can control a system while the link is up. Now, getting a little bit more, this picture was actually the one that I was referring to earlier, and just sort of digging into systems energy savings level a little bit more. This diagram is meant to show an example of how one might go about getting some additional power savings by shutting off parts of the system when multiple interfaces are in low power idle, for example. So in this picture, the green parts indicate like the phis are all perhaps, they're certainly capable of entering into low power idle. And when enough of them are in low power idle, then you could actually go in and shut off other parts of the system. And the whole point of this slide is this is just sort of meant as an example for system designers to go off and figure out ways to design the system so that you could get even more energy savings. Now the trade-off, if it isn't obvious, is latency. It takes a little bit of time to wake up the receiver. So as energy use decreases, latency increases. And there will be some cases where you may not be willing to accept this increase in latency. The one case that I pull out that's obvious here is what I call the latency arms race in the financial network sector, where they're not willing to tolerate any additional latency and are willing to spend lots of money to achieve minimum latency. So it's likely that EEE is not a feature that they would be considering for their networks. On the other hand, when we look at how much latency is increased by EEE, we're talking about single-digit microseconds for a 10 gigabit network, and in the order of hundreds of nanoseconds or even less with this new concept we're talking about with fast wake. So EEE for optical networks. It's currently being specified for 40 gig backplane and optical the next generation optical 100 gig, optical 100 gig. So, cycling into low power idle, it could be problematic for a laser transmitter. So, one way that we thought about to work around that is to come up with this concept of fast wake. Deep sleep, we call it deep sleep in the standard, but essentially that's the same EEE that we've been talking about all along. So the current proposal, and I call it a proposal because the standards are not quite done yet. Some of them are further along, and it's likely they'll complete this way, but can't guarantee anything. You signal the low power idle, you send this low power idle signal without shutting off the transmitter. So then the receiver can take that signal and still realize that the transmitter has no data to send. It's not going to shut off its transmitter. It may shut off other parts of the system that it can. Then the receiver can respond to that accordingly. One thing that was noted in the development of fast wake is that if this kind of interface were to connect to a network that has an optical transport network on the other end of it, that it'd have to be carefully done because there'd have to be some additional mapping between the Ethernet and OTN framing. The upside is that it makes this fast wake concept fairly simple because you don't have all those timers we had a moment ago when we were talking about shutting off a network interface, powering down the transmitter. So going back to the picture, it might look like as simple as going between the active idle mode to sending the LPI signal by itself and then back to active idle again, but that means that the systems designers have to do something with that signal in order to achieve the energy efficiency. So the potential to save energy here exists, but it's going to be essential for the network equipment manufacturers to do something with that fast wake signal. So I think it's crucial that that's going to have to be done. Otherwise, you just basically, you may save a little bit of energy, but not even as much as you would with the traditional EEE. When will this be available? So the next generation, what we're calling next generation 100 gig optics standard is currently scheduled to be completed in 2015. So these tools will become available. That's the first case where this fast wake will actually be available. And so the tools are being created now. Again, it's up to the manufacturers to make them useful for us. And it's, I think, really important that end users are asking the network equipment manufacturers to provide these tools so that we can take advantage of them. Just in terms of opportunities for development, again, this was, I'm not going to read these all off to you, but I just wanted to give you a sense of what's being developed in IEEE for Ethernet and where EEE is showing up or will show up. There's, interestingly, Ethernet's getting into the automotive field, so sometime in the next 5 to 10 years, there will be an Ethernet network running in your car. It will have some form of EEE in it. And then again, next generation 100 gig optical Ethernet's coming down the pike next year. Likewise, I think 40 and 100 gig backplane will finish late this year or maybe early next year. 40G base T, I think, is a few years out, a couple, 3 years out. And then my favorite, 802.3 BS, which is not a typo, that's really what they called it, 400 gigabit Ethernet, which just started and went into task force mode earlier this year. So fast wake is either being specified or will be specified in some of these projects. And again, it's really important if you care about energy efficiency for the equipment that you're going to be putting in your networks. It's important to talk to your equipment manufacturers and ask for the feature. But in addition to that, in the 400 gig project, for example, we're going back to take a look at how EEE works and ask questions like, can it be improved, or You know, is there a better way to do this, or should we just continue to use what we have been? One thing that's being considered, since this is a new speed and new PHY project, is considering shutting down lanes to save energy. This introduces an interesting idea, because in the example that I give here, if you have a 4x100 lane design and you decide that you're only going to have 200 gigabits per second worth of connectivity, could you shut down a couple of lanes? But it's going to be interesting. You could shut down the lanes, but how does that look to the rest of your network? And that's an open question. How do we do that? Do we continue to make it look like a 400 gig interface, but you only have 200 gigs available? You know, it's to be determined if that even happens. One thing that I thought was really interesting at the last last plenary meeting, or interim meeting rather, that Joel Gorgon had presented. For his presentation was titled 400 Gig Electrical Interface Thoughts. Joel's, I believe, a distinguished engineer at Cisco and a backplane expert. And he had been talking about a number of different ideas that he had for the next generation electrical interface. But what I thought was interesting is he said that if they keep designing systems the way they have been, that the next generation systems would approach 100 kilowatts a rack. And that's just not sustainable. You know, we can't do that. I know that not too long ago when I worked for ESNet that we were facing the same problems at a lower order of magnitude, where we're looking at next generation systems and bumping up against power constraints there. So it's a problem that really does need to be solved. So Joel suggested that using a different approach in the SerDes power, and that may lead to yet another form of EEE on the chip-to-chip interface. So those are sort of the latest things that are happening. So again, EEE will actually improve energy efficiency of internet information ICT. I'm tripping over that one. The amount of energy that can be saved by EEE depends on the amount of time that the network is not utilized. So, but the goal here, again, is to make the network energy proportional, so that if you do have useful work to be done by the network, then the energy use goes up. That's okay. You're actually using the network, but we shouldn't be burning power unnecessarily during periods of idle time. Again, the trade-off here is going to be with latency. We're talking about really in the order of single-digit microseconds or less for modern networks. And again, EEE is coming for optical networks in 2015. There's possible improvements that'll be coming with 400 gigabit Ethernet, but it's fairly new, so it's yet to be seen. Overall, though, I think things are good for EEE, but I think it's important, my sort of takeaway here is that, again, if you care about energy efficiency for your network equipment, then you really do need to talk to your network equipment manufacturers to make it happen. And that's it, so I'll take any questions. Looks like I'm done. Thank you.
Thank you very much, Michael.